So in this lecture, we are going to talk about equality constraint optimization. In the previous lectures, we talked about the unconstraint optimization, which means we only have an objective function and we want to either minimize or maximize that objective function. Here, we are going to have only equality constraints. All right, let's get started. Equality constraint optimization. So in the one-dimensional example, what we have is minimizing a function. It could be also maximizing with variables x subject to the equality constraint, which is g of x is equal to 0. So let's try to visualize this. This is x, and this is the function of x. So let's say our g of x is a function like this, and this is f of x. All right. So if we want to evaluate the constraint first, what are the points where the value of g of x is 0? This point and this point. So these are two potential options, which we call them x1 and x2. x1 and x2 are feasible points. So what does feasible point mean? Feasible point, which means they satisfy the constraint. So in this case, constraint is g of x is equal to 0. But now we have a problem with these two feasible points. If you look at these points, the only place in this function where the derivative of f is 0 is somewhere in between, which is not feasible. So at the feasible points, in this case, in this example, derivative of f of x at the feasible points is not 0. All right, now let's take a look at an example in the two-dimensional case. Two-dimensional means we have x1 and x2. So minimizing x1 squared plus x2 squared, x1 and x2. Subject to minus x1 minus x2 plus 4 is equal to 0. Right, first I'm going to illustrate the objective function. So our objective function, let's do this. So our objective function is basically a circle. So this could be 1, 2, 3, and so on. So if we find gradient of f of x, is going to be with respect to x1, with respect to x2, which is 2x1, 2x2. So the gradient of f of x is in this direction. All right, so let's ignore the constraint for a moment. So we want to see what's the optimal solution. Optimal solution without constraint. So what's the answer? The optimal solution, or the minimum value of this function without any constraints, is 0. Is x1 is equal to x2 is equal to 0, and f of x1 and x2, which is x1 squared plus x2 squared, is 0 as well. And now we want to enforce the constraint. So we already have our function. Say this is 1, 2, 3, 4. Now we want to enforce the constraint. What was our constraint? It was minus x1 minus x2 plus 4 is equal to 0. This is g of x is equal to 0 that we had in the generic problem. So all of the feasible points, all feasible points should satisfy g of x is equal to 0. All right, so let's try to draw g of x is equal to 0. So at some point, it's going to be adjacent to our function. So say there is another circle somewhere here. Yeah. So for g of x, if we select x1 to be 0, x2 is going to be 4. Select x2. So this is g of x is equal to 0. All right. So the optimal solution happens here. What's the feature of this point? That's where the gradient of your function is this direction, and this is your constraint. Right now, we want to see what is special at the optimal point. How can we determine whether this point is optimal or not? That's the question. So the answer to this question is at the optimal point, we should satisfy two equations. One, gradient of f of x plus a coefficient or a set of coefficients multiplied by gradient of your constraint is equal to 0. Also, your constraint is equal to 0. Let's go back to our example. We had different circles for our function. This is the direction for gradient of f of x. This is the direction for gradient of g of x, or our equality constraint. And these are different contours for g of x. For example, this one is g of x is equal to 0. G of x is equal to minus 2. G of x is equal to minus 4. G of x is equal to 2, and so on. So there is one point that they satisfy both of these equations. At that point, we can say that gradient of your objective function and the constraints are parallel. All right. So this was the idea behind KKT conditions. Now we are going to talk about a systematic way to determine the solution for an equality constraint optimization. So this was our original problem, minimizing f of x with x as variable subject to g of x is equal to 0. First, we define Lagrange function. So Lagrange function is defined as your objective function plus vector lambda transpose multiplied by g of x. So I'm going to talk more about the vectors, matrices, and all of these matrix algebra in the introduction to linear algebra part, which is the next video. So after we define the Lagrange function, we want to minimize the Lagrange function. Minimize Lagrange function. So in order to minimize Lagrange function, we simply find its derivative with respect to x and put it equal to 0. We find its derivative with respect to lambda and put it equal to 0. So let's see what's the answer to each of them. Derivative of Lagrange function with respect to x is going to be derivative of f of x with respect to x plus lambda transpose derivative of g of x with respect to x equal to 0. Derivative of Lagrange function with respect to lambda is going to be g of x is equal to 0, which is basically our equality constraint. So if we can solve this set of equation systems, then we can find the optimal answer. All right. Let's say number of variables is equal to n and number of equality constraints is equal to n. In this scenario, this is going to change to an equation system which has n plus m variables and n plus m equations. What does that mean? That means there is only, if this problem has an answer, it's going to be a unique answer. What do we call this? We call this KKT, which stands for the name of people who invented this. First order or necessary conditions. All right, so what are KKT conditions? KKT conditions are the conditions that guarantee that for an equality constraint optimization, the solution is going to be optimal. All right, let's see what's the meaning of the Lagrange multiplier, because lambda is called Lagrange multiplier. So if you look at the discrete scenario, and not the derivative, just the discrete scenario, instead of derivative of f with respect to x plus lambda derivative of g of x with respect to x is equal to 0. Let's say delta f of x by delta x plus lambda delta g of x delta x is equal to 0. This is for the case where delta x is a very small value. So in this scenario, let's see what's the value of lambda. We have lambda delta g of x divided by delta x is minus delta f of x by delta x. So these two cancel each other. Then lambda is minus delta f of x divided by delta g of x. So this Lagrange multiplier corresponds to the negative sensitivity of the optimal objective function value with respect to a small change in the equality constraint. This is the small change that I talked about. So if I want to talk about this in the real world scenario, it means what will happen if you make a small change in your constraint, how it's going to affect your objective function. Let me write it here. Lagrange multipliers correspond to the negative sensitivity of objective function. What's the objective function? F of x. What's the sensitivity of objective function? Is delta f of x with respect to small changes. What's a small change? Delta x, which is close to 0, in the equality constraint. So what's the small change in the equality constraint? It's delta g of x. All right, let's go back to our original problem. Our example was minimizing x1 s2 plus x2 s2 subject to x with variables x, where x is x1 and x2, subject to minus x1 minus x2 plus 4 is equal to 0. You want to write the KKT conditions for this optimization problem. All right, first we have to write the Lagrangian. Lagrangian was f of x plus lambda transpose g of x. In this case, because we only have one equality constraint, then our lambda is going to be, instead of being a vector, it's just lambda 1. So it's going to be x1 s squared plus x2 s squared plus lambda multiplied by g of x minus x1 minus x2 plus 4. All right, so our KKT conditions are derivative of Lagrangian with respect to x1, which is 2x1 minus lambda. This one should be 0. Derivative of Lagrangian with respect to x2, which is 2x2 minus lambda. This one should be 0 as well. And finally, derivative of Lagrangian with respect to lambda. For this one, actually, we can use our equality constraint as a note, because this is exactly going to give you your equality constraint. Minus x1 minus x2 plus 4 is equal to 0. All right, what do we have here? We have a set of 3 equations with 3 variables. What are our variables? x1, x2, and lambda. If we solve this set of linear equations, it should give us the optimal answer, the optimal solution for the original optimization problem. So these 3 conditions, these 3, this one, and this one, are called the KKT conditions for our original problem. We also call them KKT first order or necessary conditions for equality constraint optimization problem. All right, just to wrap up this lecture, we talked about minimizing f of x subject to g of x is equal to 0. We call this equality constraint optimization. Then we talked about how to solve this problem, KKT conditions. In order to write the KKT conditions, first formulate the Lagrange function. How do we formulate the Lagrange function? It's your objective function plus lambda, or a set of Lagrange multipliers by the equality constraint. So we call this Lagrange multipliers. And then in the next step, in order to find KKT conditions, we find derivative of lambda with respect to x, and we put it equal to 0. Find derivative of lambda with respect to L, Lagrange function with respect to lambda, also 0. The second one basically gives you g of x is equal to 0 for your equality constraint. This is gradient of f of x plus lambda transpose, gradient of g of x is 0, and g of x is 0. So that was all for this lecture.